Hey everyone, Dr. Calkins. This is week 16, chapter 11. This is the student's favorite homework, only because it's the last one. We don't have to do any more. So when we do this one, we need to pay attention to the three types of problems in this chapter. Does it have STP? If so, mole conversion. Does it have one of each? If so, single chart kind of problem. Does it have two of each? Double chart kind of problem. That's the approach we're going to take as we dig through this homework, unless it's, say, a definition or concept. So as we look at number 5, it says, what is the value for R? R is what's used in the ideal gas equation. That's the PV equals nRT. So there's the R that we're looking for. And R is what we're using in every problem. And it only has 1 0 in front. So we're going to get that one for free on the final exam when it's important. But it is important to do it on several problems coming up, especially the one coming up next. So number 6, notice we have one volume, one pressure, one temperature. If we only have one of each, we're going to do a problem that uses only one of each. So PV equals nRT, the ideal gas equation. If we do a single chart, we're going to fill it in, solve for the variable that's missing. So we have a pressure of 0.335 atmospheres. R is 0.0821 liters times atmospheres over moles times Kelvin. And notice atmospheres and atmospheres match up, so check. Volume is 5.5 liters. And liters match up, so check. No moles mentioned, turns out that's what they want. So there's our question mark. And then the temperature is 25 degrees Celsius, which is a problem because R uses Kelvin. So we're going to add 273 to convert it. That's going to give us 298 Kelvin. We're going to need that number instead. So we're solving for N. We need to divide both sides by RT. R's will cancel, T's will cancel. So N equals PV over RT. And we'll just plug in our values straight into this formula and throw them into our calculator. So our pressure was 0.335 atmospheres. Our volume, 5.50 liters. We divide that by R, which is 0.0821, only 1 0 in there. Liters, atmospheres, over moles times Kelvin. And then our converted temperature of 298 Kelvin. So notice Kelvin cancel, atmospheres cancel, liters cancel. All that's left is moles. If you're on the bottom, you're really on the top in algebra. So any of that sounds. So 0.335 times 5.5 divided by, open parentheses because of PEMDAS, 0.0821 times 298, close parentheses, it equals 0.075. And that's what we're looking for here. Number 7, exactly the same, but with an extra step. So they want the weight of nitrogen gas. In order to get that, we need moles, which is what we just did. The reason I chose these problems is because it's very similar to one of the final exam questions where you solve for N only. So one of the final exam problems is just like number 6. Number 7 is just like 6, but it has that extra step, which the final exam problem will not have on it. So PV equals nRT, and I believe this is 52 in the final exam. So again, single chart. The reason we know that is because one volume, one pressure, one temperature. So we know it's a single chart, not a double chart. So PV, N, R, and T. R is a constant. You can go ahead and put that in always. Pressure is 1 atmosphere. Volume is 1.25 liters. N is missing, so again, that's what we're looking for, moles. Temperature is in Celsius. Notice R is in Kelvin, so we have to convert that one. 200 plus 273 gives us 473 Kelvin. Same thing as before, divide both sides by RT, so again, N equals PV divided by RT. RT on both sides, cancel on the right side and on the left. Plug them in. Pressure is 1 atmosphere. volume is 1.25 liters. Next is R, 0.0821 liters times atmospheres over moles times Kelvin. So far, atmospheres and liters have canceled. And then we need Kelvin. So that was our 473 converted temperature. Kelvin cancel, and now we're at moles again. So this is not the answer, it's step 1 of the answer. So we have 1 times 1.25 divided by open parentheses 0.0821 times 473, close parentheses. Don't get too excited, this is moles, this is not mass. So 0.0322 moles. Mass would be moles times grams per mole in the periodic table. So in 1 mole, what is nitrogen gas? That would be N2, so that's N plus N. Nitrogen on the periodic table is 14. 2 of those would be 28. So there's that second step that's not in the final exam, but is in this particular question. So we're going to take that number we just had, times it by 28, and get the mass of nitrogen gas to be 0.9. Alright, so number 11. Notice this one says doubled. So we could use kids in the playground, or we could just use math. Either way it's going to work. But because it has doubled, we're going to know it's going to use the double chart. So here we're going to take a chart and have 1s and 2s, P's, V's, N's, and T's. Here they say that both temperature and volume are doubled. So the easiest way to double is just to use a 1 and a 2. Temperature is doubled. Again, they said volume is also doubled. What happens to pressure? So moles wasn't touched, so we won't use moles. This one is much like our lab experiment 24. So we have P1 V1 over N1 T1, P2 V2 over N2 T2. You get all these formulas on the final exam, you just need to know how to rearrange them from our charts, plug in the numbers, and dump them into your calculator. We want P2, which is over here. Easiest way is to get rid of N first, because it's not being used. That simplifies it a little bit. We're going to cross multiply and then divide, so P1 V1 goes down with T2. That's going to equal P2 V2 multiplied by T1. We still need P2, so let's divide by V2 and T1 on both sides. Notice this gives us volumes and temperatures top and bottom so that their units cancel. Now let's plug into our chart. So pressure 1 is a 1, volume 1 is a 1, temperature 2 is a 2, volume 2 is a 2, and temperature 1 is a 1. All of that equals P2. This ends up being 2 over 2, which is just 1. So what this tells us, and this is exactly like 51 on the final exam, this tells us that pressure ended up as a 1 and started out as a 1. So to us, that means it remains the same. This should make sense with our kids in the playground analogy, because if you double the size of the playground, that would make those kids run twice as long across it. That would cut the pressure in half. Pressure and volume are inverse, and doubling the volume cuts the pressure in half. But if you speed those kids up twice as fast, that will make up for that reduction in pressure by increasing it. So pressure and temperature, those are directly related, so they're directly proportional. So if you double the temperature, you double the pressure. So volume's cutting it in half, but temperature doubling it, it's like it never changed. So that should make sense both mathematically and by analogy. Number 12, looks like the word double's in there again. So that tells us we're going to use our double chart once again. So let's do a double chart, 1s and 2s, P's, V's, N's, and T's. A gas sample occupies a volume of 8 liters, so 8 liters at 20 degrees. at 273, which is 293 Kelvin. The temperature at which the gas doubled its volume, so 16 liters. What is the temperature? So notice they did not mention moles, and they did not mention pressure. So we can ignore both of those and remove them from our original equation. So we have P1, V1, N1, T1, P2, V2, N2, T2. Since P's weren't used, let's get rid of them. Since N's weren't used, let's get rid of those. And what we want is this final temperature. So unfortunately it's on the bottom. That makes it very painful, so let's cross multiply and divide again. So V1 T2 equals V2 T1. Still need T2, which is over here, so divide by V1 on both sides. These cancel. Now just plug them in from our chart. Temperature 2 equals the volume 2, which is 16 liters, times the temperature 1, which is 293 Kelvin, and then volume 1, which was 8 liters. Liters cancel. And then it's just a little bit of math, so basically just cutting that one in half. 16 times 293, and then divide by 8. So it's doubling it. 16 over 8 is double. So 586. Okay. So it should make sense with our kids on the playground idea. If pressure was the same, because it didn't change, or they would have said so, the volume would have cut it in half. So in order to make up for the volumes doubling, which would reduce the pressure by half, we're going to have to double the temperature to make it move twice as fast across that space in order to maintain the pressure beginning to end. So it's very similar to the previous problem, just with real numbers. So that was 586. Number 14. Number 14 says, in this situation, it says it's final. So final just means before and after. That means double chart problem once again. So P's, V's, N's, and T's before and after. So in this situation it says pressure and quantity remain constant. What will be the final volume of a 4.86 liter? So final volume. If we went from 281 to 300. Again, these are in Celsius, so let's add 273 to convert them to Kelvin. So we have 573, and then 554. So P1, V1, N1, T1, P2, V2, N2, T2. P's and N's didn't change again. We need volume 2, which is up here. So very similar, but the reverse of the last problem. So let's cross multiply. V1 T2 equals V2 T1. Get V2 by itself, so divide by T1. These cancel. So now let's just plug it in from the chart. We have V1, which is 4.86 liters. And then T2, which is 573 Kelvin. And then we have 554 Kelvin for temperature 1. Kelvin cancel. So 4.86 multiply 573 divide by 554. About 5. And what's closest to 8? Within rounding, now it's 5.026. Number 15, that says final again. So rinse and repeat of the last one. If there's a final, there's an initial. So double chart. 1s and 2s, P's, V's, N's, and T's. Here it says 1.6 liters. We have 330 Kelvin, which is nice, it's already in Kelvin. We have 4.84 atmospheres. When the volume was reduced to 840 milliliters, that's a trick question because that's really 0.840 liters. Milliliters and liters are not in the same unit, so they need to be. So divide by 1,000 and move that decimal point back a few spaces. So there's a trick to that one. It says in the beginning that temperature and quantity are remain constant. So it was 330, it's going to stay 330. So those are irrelevant. What really is important here is our final pressure. So P1, V1, N1, T1, P2, V2, N2, T2. Now we see the N's and T's, which are the denominator, unimportant. We want pressure 2, so let's just divide both sides by V2. V2 will cancel. So P1, V1 over V2 equals P2. Plug it in from our chart. So P1 is 4.84 atmospheres. V1, 1.6 liters. V2 is our 840 milliliters converted to liters by dividing by 1,000. That's 0.840 liters, so that liters can cancel. Otherwise, you get the easiest wrong answer, which is probably a choice because the textbook is mean and likes those kinds of tricky kinds of questions. So 4.84 times 1.6 divided by 0.84, and we get 9.2. So in 16 we did a different kind of problem. It's conceptual, which is most of the rest on this page that we're asked about. Molar volume for an ideal gas is 22.4 liters, but it has to be at STP. STP is standard temperature and pressure, which is 0 degrees Celsius or 273 Kelvin. Also 1 atmosphere or 760 millimeters mercury, 29.9 inches mercury, so on and so forth. So it's very specific to STP only. So 22.4 liters only works at a specific temperature and pressure. If you have a different temperature or a different pressure, that's when we use the ideal gas equation to find volume, because it will no longer be 22.4. So in 18, it says which of them have the smallest volume at STP. These are definition based, but I can walk you through what they mean. So here with Avogadro's number, so this is equal to 1 mole, and 1 mole equals 22.4 liters at STP. So A is 1 mole. It's also important to know that as we look at something like this, chlorine is 35.45, but this is Cl2. So what this is relative to is half a mole. If this is half a mole, this would be half, or 11.2 liters at STP. So if 1 mole is 22.4, this would be half of a mole, or half of 22.4, which is 11.2. So far, the smallest. If you look at this example over here, hydrogen is 2.02. This is about 4.04 roughly. So this is about 2 moles, and if 2 moles is at STP, that's going to be 2 times 22.4, or 44.8 liters, which is so far the largest. And then down here, this is 1 mole. If it is 1 mole, 1 mole is always 22.4 liters, the magic number for this chapter at STP. So this is tied with A. So this is 1 mole. This was about 2 moles, and this was about half a mole, and that's why this one is the winner. It's got the least amount of moles, so it's going to have the least amount of volume at STP. 21 says volume occupied. Typically, if we saw this kind of problem, we would do PV equals nRT and solve, but in this case we don't have to because it says STP. We can just say if it's 4 grams, this is how a lot of the matching sections are on the back of this homework. If you have 4 grams of O2, which is oxygen gas, get rid of it. Grams of O2 per 1 mole. This would be O plus O, that's 16 plus 16 on the periodic table, that's 32. And 1 mole, we now know that there's 22.4 liters of gas at STP, but again, it says STP, so we're good. grams cancel, moles cancel. Now we're ready for the calculator. So much faster at STP because we have the specific volume. So 4 times 4 divided by 32 times 22.4. So 2.8. Very similar on the bottom. It says STP again. So if we have 3.01 times 10 to the 23rd molecules, we know that Avogadro's number would be 6.02 times 10 to the 23rd molecules per 1 mole. And we know now also that 1 mole is 22.4 liters at STP, but again they said STP. So we don't need to use Pivnert. We can use the magic number directly because it's at STP. So 3.01 second x to the 1, 23, divided by 6.02 second x to the 1, 23, times 22.4, and we get 11.2 because we had 3 over 6, which was really just half. So 11.2 liters. Number 27 says, the term elastic says that no kinetic energy is transferred during collision. This is one of the assumptions of an ideal gas. That means if you hit a deer with your car, there's no damage to the deer, there's no damage to the car. In reality, that doesn't happen. But for gases, we assume it happens so that there's no energy transfer when a molecule strikes the container, causing pressure, that kind of idea. So this is true. Elastic is just like a waistband, it stretches in and out. We're assuming that no energy is released in that process. Number 30, it says inches of mercury equals to atmospheres. So 30.19 inches of mercury. There's 29.9 inches of mercury per 1 atmosphere. That was the definition at the beginning of this chapter. So as long as that equals, when we divide 30.19 divide by 29.9, we get 1.0 about 1. So it looks like that's about a perfect match. So true. Within round. 33 says molar volume of any gas is equal to 22.4 at any temperature. Well, that's the problem. It's not at any temperature. It's at 0 degrees only, or 273 Kelvin, which is the same thing. So as soon as they said any temperature, it became false. Molar volume of water vapor at its boiling point is 22.4 liters. Well, that's wrong for the same reason. You wouldn't have water vapor. It would be water at 0 degrees because 22.4 only works at STP, which is 0 degrees, 273 Kelvin, no matter what. So it could be water, could be oxygen, could be ozone, doesn't matter. What does matter is the temperature is specific and the pressure is specific. Grand finale. Last 3 problems of the semester that were asked. Keep in mind this lower section were problems like what we just did with our moles and grams, 22.4. So anything down here, 22.4 liters is the major conversion, and also use molar mass. For these, a little bit different. A couple of these in the multiple choice that we skipped over. Density is molar mass over molar volume at STP. So if density is molar mass, we just need the periodic table divided by 22.4 liters per mole. So again, this will be in grams per mole. We just need the specific example. So here we have C2H6. So 2 carbons at mass of 12.01. So 24.02. And then we have 6 hydrogens, so plus 6 times 1.01. So we get a 30.08 grams per mole. That's again C plus C plus H plus H plus H plus H. And then we divide by 22.4. We can do that because it's at FTP. We get 1.34, which is straight across. Notice when this happens, this is liters per mole, so moles cancel. We get grams per liter. And that's density for a gas. Neon a little bit easier in this situation because neon is just an element, so we can go directly for its mass, which is 20.18 grams per mole on the periodic table. So this is just neon. Since it's at STP, we can use the same molar volume. Moles cancel, we get grams per liter again. So 20.18 divided by 22.4, and we get 0.90, which happens to be straight across. So now we know that this is the last one. This would be carbon at 12.01 plus 4/19 divided by 22.4 liters, and you'll get the last answer of the homework to the last homework, and we're done for the rest of the semester. Good luck on your final.